All right, picking up where we left off, because I am a big silly girl and I pressed my iPad off screen, so I stopped screen recording. Anyway, picking up where we left off, we had just created our three hybridized orbitals that we call the sp2 orbitals. But remember, I said that orbitals are conserved, meaning I can't just get rid of an orbital or add an orbital for my own convenience. So I have to consider the fact that there is an unhybridized p orbital that's left over. So I'm going to include this in my energy diagram. It didn't go anywhere, it just was not involved in the hybridization process. So this is my 2p. Now, boron had 2 electrons in the 2s and 1 electron in the 2p, so that's 3 total valence electrons on boron, meaning I can now fill my hybridized and unhybridized remaining orbitals with electrons, following my normal convention of filling 1 electron per orbital until I have to double back and double fill. Here I've only got 3 electrons, right? 1, 2, 3. So I have filled all of my sp2 hybrid orbitals. I have not filled this unhybridized p orbital. And if we were to look at how this would allow for boron to form, bonds to hydrogen, I'm going to again recycle my axis here. So my hydrogens each have 1s orbitals containing 1 electron. And my boron, that contains my, nope, not 2s, we've hybridized. My sp2, that is too big. And my unhybridized 2p orbitals with 1, 2, 3 valence electrons placed in each of my sp2 hybrid orbitals. So now I am looking for half-full orbitals that can overlap with one another, and in doing so, form a spin-paired electron cluster, which is what we call a bond in valence bond theory. So I definitely seem like I can do here, here, and here. Ooh, and that seems like I can at least fill up all of these sp2 orbitals by creating 3 overlapping orbitals, or 3 sigma bonds to hydrogen. So if I were to draw this according to Lewis conventions, I would have boron singly bound to my 3 hydrogens. And this is where we see why boron is an exception to octet. This hybrid orbital is completely full when it bonds to 3 hydrogen atoms. And because of this hybrid orbital being completely full, we're stable. Now, if this was half full and needed to be paired, that'd be another story, but there are no electrons in this unhybridized p orbital. So since we have managed to completely fill up our valence orbitals that were occupied in the first place, then we have now created a stable electron configuration. So what would this look like if we actually drew the orbitals out? Okay, so we've got boron here. That is a giant minor lobe. There we go. And I'm going to draw this in my flat triangle way, like so. Like I'm not going to draw it planar. I know that I just kind of contradicted myself. So that's going to look something like this. I'm going to have an sp2 orbital that comes out of the screen, an sp2 orbital that goes back into the screen, and then an sp2 orbital that kind of is just hanging out in the plane of the screen. So this is my triangle oriented in the XZ plane. So if you think about Cartesian system, the XZ is this plane here. So that's the one that's flat. So that's what I'm trying to do here. Okay. So here's my boron with its Sp2. No hybrids. Let's see if it comes back. Sometimes it does. Sometimes it's just a bother. Oh no. Okay. It's all right. We can improve our artistry. How's that? So here's our minor lobe. The things I do to make chemistry beautiful for you. And then we've got our lobe going back, and then our lobe coming out. That is awful. Yeah, it's a little better. Okay. Okay, so these are each my sp2 hybrid orbitals. And according to this orbital box diagram here, each of those sp2 orbitals contains one unpaired electron. And then if those were to bond with hydrogen, where each hydrogen contains its own unpaired electron, we would form spin paired electrons in that overlap region, which is what makes this a bond, these overlap regions. And let's think about the left out little unhybridized P. So I'm going to not pick green because I've got a lot of green going on down there. Let's do, what don't I have down there? Because I don't have, well, I've done red up here. Okay, I guess blue. We're doing a very cool toned palette. So this unhybridized P, what does that look like? Well, not that exciting. It's exactly what you'd imagine. I've got my regular p orbital, which is not my hybrid orbital, peeping up, up, down. And remember, this is because I explicitly said earlier that it was my px and pz, which is why I'm drawing this flat in the xz plane, that we're going to be combining with my s to make my sp2 hybrids. This now shows that my py is sticking up and down in the y axis direction. And this is what we got going on. So hybridization and valence bond theory explains the weird exceptions to octets like we've seen with boron. Oh, and since we haven't written it out, this geometry is a flat triangle. So let's call it such, trigonal planar, because we are looking at an sp2 carbon. So anytime you see an sp2 carbon, you should be saying, okay, that is trigonal planar in orientation in space. Now scroll up. Okay, I think I have probably done enough talking for this lovely Wednesday. So let's go ahead and save this whole concept of pi bond formation, which happens with both sp2 and sp hybridization, for Friday. And once we've discussed pi bond formation, aka where do double bonds factor in valence bond theory, on Friday, we will move into our final model of bonding, which is kind of the accepted most reliable bonding model, which is known as molecular orbital theory. So this is why I've been saying atomic orbitals instead of just orbitals in this lecture, because at some point we do need to make the distinction between orbitals that are located around single atoms and orbitals, molecular orbitals, that are dispersed across the entire molecule. So this is it for Wednesday the 8th. I shall see you in our bonding lab workshop tomorrow to discuss VSEPR theory, and then in office hours on Friday. Thanks, folks.